All right, guys, we are back for video number 6 here. Claudia's going to kick us off with this is the next transition. We just finished up with trigger, and it's going to be a fun recap. Just kick it off,
Yeah,
buddy.
I mean, I know you didn't want to talk about this again. I just wanted to do it one more time with steps. So I'm gonna do a little quickie thing here and share the. We go.
So we're recapping these every time we're posting these up. We're just trying to improve on our own output, so you guys are seeing the better quality improve every video. Claudia's going to show a better picture because when my screen goes, the output is let's just say a little bit less than ideal for screen sharing.
Yeah.
Go ahead, buddy.
All right. So in a quick summary, just 4 quick points that I wanted to cover here. We've got the determining what your trigger sensors are, what your crank and cam sensors are, whether the reluctor, whether the Hall. You need to figure out your pinout so that you know what you're wiring and where it goes, and so on and so forth. So once you've determined that, you've hooked everything up, and then the thing you want to do is obviously you go into your trigger setup, and I'm going to quickly here share a little window with some basic trigger settings to just go over real quick. So in this example, I've basically got it's interesting engine. It's a 1GR Toyota, but any engine will obviously be done in the same way. You've got your engine type selection, or you can go through the wizard, which is the button that's up here. Ideally, if you go through the wizard, it'll be a little easier for you because it'll populate all the settings. But if you're starting from a base map, then obviously this will be set up as well. But quickly is the stuff that isn't this grayed out, you just don't need to worry about it because the software understands what it's been set to. The most critical value that you have to look at is your TDC angle, which tells the ECU where TDC is. And this changes from engine to engine. However, engines that are the same from one model to another and haven't been modified with a different or custom crank or cam sensor will always have a very close, if not the same value. I personally always recommend the quick start mode to be disabled. That way you won't be sabotaged by wasted spark and you really can't exactly tell where TDC is. You could be under compression or under exhaust. So for the time being, quick start should be turned off. That way it'll be in sequential mode and you'll be able to properly fire at TDC compression for cylinder 1. Then eventually you go through your crank and cam sensor. What type are they? You set these up. Then you connect your timing light, and then it's time to move on into the ignition setup, configuring your coils and going through that. Now, here's something that I want to basically kind of bounce back and forth with you, Ryan, is how about we talk a little bit before we start on settings about ignition coil requirements based on power goals and expectations. Your fuel is the engine 100% street car, and by definition, a street car has AC and power windows. You don't got AC, if you got Lexan and you got no interior, it ain't a street car.
Good point.
So if the car is going to be driven on the street or the car is going to just go all out on the track, what fuel is going to be used and how much boost you need to use, that'll determine what kind of an ignition system you need to keep up with power.
That's right. Weak ignition will be the end all of engines, right? You can have all the fuel in the world and it doesn't matter if you're using...
You can't light it up.
Yeah, you get 18 gauge wiring to power your ignition 1A coils. And while these are a very strong non-CDI smart coil that has a very long duration spark, the downside is that when you have, let's say we have a rotary engine, which we're all very familiar with, rotary engines are using twice the spark in that given period of time. And I actually have a sheet that I did way back when that I'll bring up on screen later when we get into this more in detail. And it goes through how a charge time will now change because the period in which the engine is able to charge for our, we call it spark dwell time, is now half of that of a reciprocating engine. And because of that, Claudio, you know this just as well as I do, the wiring required for that coil, because the amperage is now much higher, has to be a much larger gauge wire to account for that. So it's one of those things where, again, we're doing it based on the application, and some things will require CDI, because if you're aiming for 3 to 4 times over a factory power output, why trust it with something that is only good for maybe 75 millijoules of energy at redline? Just doesn't seem like a smart approach.
One of the things that we probably tell our viewers is that there is a really, really top-notch comparison test video done by the boys at Platinum Performance down in Australia. We should probably put up some links somewhere, maybe in the description. We should have a link to that video. They went and just got every single coil that everybody always raves about. They got the knockoffs, they got the original ones, and the variations that are also good quality, because you could either have the same coil done by NGK or done by Delphi, and they're both will be good, but there will be differences. And they basically went through them all and rated them as higher the power output that they can handle. And the bad boy of the bunch is the IG1A. Yeah. Second place goes to the R35 coil, the GTR coil, which is really good.
That's half the power of the Ignition 1A's R35 coil, just to put that in perspective.
There's also the quirk about power requirements. Ironically enough, the R8 Volkswagen coil, the red coil, it's good, but it's a power hog, and it's not as powerful. But it's not as powerful as the IG1A. So that video is an awesome insight into what coils you can use to get away with on a street car, whether you have a Subaru, a Honda. Strangely enough, they never did the K-Series. I guess the engine isn't that popular in Australia. We'd love to see what the K-Series does.
Incredible. I'm surprised. So
yeah,
one thing that really needs to be thought about is what I was saying with engine period duration. So with RPM, we have a certain amount of time that the coil is allowed to charge. And some coils are going to be a very long duration spark. And some ECUs are not, let's just say they're not smart enough to maintain and shrink that spark duration with RPM. And so they may have, if we have a smart coil that's sending out, let's say,
there you go,
an Ignition 1A, Lance's data sheet is 3.2 milliseconds plus or minus 10% for duration of spark. Now, this is not this dwell table that Claudio's brought up. This is the duration of the spark event in total. A CDI, by comparison, will have a 0.2 millisecond on average spark duration. That is the time in which it is giving off the energy, and the energy itself being produced is pretty much, it has to be a measured by clamp force number. And what we'll do is we're going to go over how the engine period can dictate if you want to go with an Ignition 1A, an R8 coil, R35 coil, CDI, or any other distributor style ignition.
There's also the quirk about what coils you need based on your shaft length or your depth of the spark plug hole. Some coils just don't reach down there. Obviously, with the IG1A, you need a really long boot, and there's spark plug cables for those. But some people just don't have the room in the engine bay to mount the bracket with the 4 or 6 or 8 coils, and they'll need some solution that's a more coil and plug. Now, this table that I've loaded up here, it's an example of how roughly to set up an IG1A coil on a rotary. That's why you see such high numbers, because these things, first of all, they're firing twice as much, and obviously they require a much higher dwell to keep up with demand. And on a 500 horsepower motor, you know, you do need the spark.
So using Claudio's table right here, I'll give you a number off the top of my head that I know. So at 9,000 RPM, we have 6.6 milliseconds of total period time in the engine. Now, if we are charging the spark for 4.63 milliseconds, that means that the leftover duration of that is going to be the spark energy. And our total duty cycle is actually going to be exceeding what we should be aiming for a threshold. So that's why the ignition 1As don't really last very long at high RPM for rotaries. We're pushing them past their intended boundaries. So if you do,
And there's also a factor that needs to be accounted for, which is the off time. There will
that's what
be
I'm saying, yeah.
eventually a complete off time where the coil is not firing nor charging, which
So
is
let
the
me
in between.
go ahead
Spark it.
and I'll pull up
I'll,
one of
I'll, I'll
my
take it off.
data sheets. Yeah.
Yeah.
That way I can kind of give them a heads up. This is going to be my.
While you do that, I'll tell you what, I'll just go over real quick the basic settings for most applications. So just to go back and talk a little bit about the ignition settings. Again, here we are under engine configuration, engine ignition system, and then we have the main settings. Now, there will be specific ignition modes, and the ignition mode is dictated by the number of coils you need to fire and the number of cylinders. If you have a single coil distributed motor, obviously your mode will be distributor. If you have a dual coil, dual post coil, or you're firing two cylinders at the same time, your mode then will be direct fire. Wasted spark. And then direct fire will be for individual control of the coils. Then you have stuff like twin distributor or single wire CDI, which is just options available for more flexibility. Say on a big V12 engine, like out of an old 850 BMW that has two distributors on it, or a Toyota. I think the earliest iteration of the 1UZ was a twin distributed motor. Stuff like this will let you just fire two ignition outputs, one for each bank. Then eventually you have falling edge, and this is where the coil will discharge. 98% of all stuff is actually falling edge. The only examples I can remember of rising edge on an ignition module are a very old Bosch module that used to be used, but it's no longer available, and the Honda B series and D series built-in igniter for the distributor on those B and D engines. Then we have the dwell mode, which for the regular coil families are just constant charge, but if you're using a CDI, then you would also use constant duty, and then the settings would be slightly different. In constant duty, you don't use a dwell table, you use a period. And basically you're just telling the CDI box to fire essentially half the time, and then the CDI takes care of the rest.
So on that, a rotary cycle period I'm using as T in this calculation is 60 divided by RPM. So let's say we've got 3,000 RPM at the engine's rotating speed. That gives us a total duration that you can do any spark event is 20 milliseconds. The spark event for the standard coil is actually rated at 3.2 milliseconds. So that's leaving us with 16.8 milliseconds of real usable duration. Now,
but that's low RPM, of course, we really don't need that.
But that's where I'm just going to explain how the coil charges. So at 80% duty cycle of the coil, we would have a total availability of 13.44 milliseconds of usable dwell time. Okay, because we're subtracting the actual spark duration from the dwell time. So you can see that number quickly dwindles. And at 9,000 RPM, our total charge time, if we leave the spark duration at 3.2 milliseconds, then we're stuck with a very short amount of time to charge because it is not enough total time left for the coil. What this can do for some ECUs is this can overlap the ignition event into the next combustion chamber, the next ignition event. And
Not
because
all
we
ECUs.
only have
Not all
2.7.
ECUs.
That's what I said for some. And because we only have 2.7 milliseconds of charge timing, we're only outputting, instead of a 164 millijoule that we would have at full charge when it reaches its it's a dilution point. What was that called?
The saturation point.
Saturation point. Once it reaches its saturation point, we're good up to, on this application, about 4,500 RPM. By maintaining 80% duty cycle on that coil, that drops down to 55 millijoule of energy at 9,000 RPM if you're maintaining this spark duration. Now, I know specifically on Link ECUs, you can somewhat set this to a maximum spark duration or a minimum spark duration, depending. I have to go pull it up and double check. But I know that it does dwindle it down for you, and therefore our numbers can now maintain, instead of 2.7, they can maintain something around 4.5, 4.7 milliseconds. So the ECU should be reducing the spark duration number internally. However, we never have control of that. So what I would request is for ECU manufacturers to actually give us control of a spark duration table. And so when we do our coil control, we're actually referencing not only our dwell time, but our spark duration that we're telling that spark to event to work at. Because personally, I found that if it tries to maintain it, we're going to be overlapping into the next combustion event. If we're allowed to reduce this value, like what I did here, let's say 1.2 milliseconds, well, now we're up to 4.3 at that same 80% duty cycle for this. And now we've gone from 55 to 86 millijoule. It's a huge jump in power. That's enough to cut through probably another 6-7 pounds of boost. So Claudio, take it away.
Yeah, so effectively what we're saying here is there will be certain limits to the amount of dwell time that you can use in any given motor. And even if the coil will take it, even if you put the coil in a simulator on a bench and you get it to rev up to 16,000 and still work normally, you would still be reducing the amount of charge time that you could actually get the coil energy up and usable. So that's effectively causing you to lose spark at the higher end, at the higher boost levels, and cause misfires and get the engine to not rev past a certain point. So be mindful of this. Usually a good tuner will have some examples of popular coils for the majority of the applications they've done. But again, if you would really like to figure out what the maximum allowable charge time or saturation point of a coil is, you would need an oscilloscope, a high current clamp, a bench setup. It's a little complicated. But again, that Platinum Performance video is a wealth of knowledge and information on the inside of more of the popular coils that everybody uses.
I'm going to find it right now just so they can see it. I think they have 17 different coils or something. It's quite an exotic testing.
Yeah,
They did a good job.
We can link it in the description. I'll find the video, or if you find the video, just link it on the bottom there. We'll have it ready for you. So moving on, once you know your settings for your coils, once you have your ignition mode figure out, once you have the firing order of the engine is key, you need to input that in the main setup of the software. One thing to note here, some ECUs have a fixed firing order of ignition coils, and it's hardware dictated, meaning your coil number one output will fire first, then the second, third, fourth, and so on. And the ECUs will not have a firing order selectable. These days, most ECU manufacturers will allow you to just wire up the individual coils outputs to each cylinder corresponding number, and then you just change the firing order in the software, and the ECU will alternate, what coil to fire eventually. So once you've got your firing order dialed in, you've wired your ignition coils correctly, you've made sure your engine is properly grounded to battery, and you've got proper power going to everything, and your wire gauge is correctly set, and your spark plug wires are the right wires for the job, then we can put the timing light on there. We can set our lock timing feature, which is what we discussed earlier. You make sure that you've got a mark on your crank pulley, let's say of 10 degrees, like most Toyotas or most engines, and then you lock the timing at that value. And you want the non-adjustable timing light. If you have an adjustment on your timing light, you set it to 0. You want to look at where the mark goes to at 0 or at 10, and it doesn't deviate from there, so you can increase or lower your trigger angle to match the timing. Once you get the timing mark done, and you're able to do this during cranking most of the time, then you can move on to the injection system and the sensors and connect everything to try and fire up the engine. Don't try to connect everything and try to fire the engine without figuring timing first. This is one of the most critical and common mistakes people made. They don't have the right settings, and the engine's just getting flooded. Your spark plugs are dying. They're getting, all soaked up and shorted. It's not happy.
So I just pulled up here behind you, Claudio.
Yeah, I got it.
The amperage rating for a given wire size for TEFSOL.
Yeah.
This is the one I used all the time. I know everyone uses something different. It's just real quick and dirty, giving you an idea of what sort of amperage you can expect. So like those Audi coils that are extremely power hungry at only, it's like 2.4 milliseconds of charge time. So again, that would actually be effective for some rotary stuff because you don't run out of time.
But the coil
amperage
demands
draw,
a bunch of power.
and it's like 24 amps per coil. It's
No,
like
it's not that much. I think it's like in the neighborhood of 10, but it's still way more than an IG1A. It's ridiculous.
Well, it is ridiculous. The one that is the most ridiculous is the Eagle, which I think I had up on my sheet. It was something like at 2 milliseconds, it pulls 25 amps. And I believe it is actually the Audi based into the Ignition 1A body with a different cooling package. So when the dwell is brought up, it will go up past 10.
Question about this chart. Is this taking into account a specific length? I can't.
It is not. So you also have to have the deduction of the length of the runs. So this is assuming a short wire. I'm assuming probably under 4 to 5 feet. And then when you go past that is, of course, when you're going to have more and more drop.
I use a calculator that I have to assume it is a bit overly exaggerated, because I love to use it because of this, because it tells me sort of a big dramatic drop in voltage. So I'm always oversizing my wires. I'm paranoid about voltage drop.
I would be too. My car is
so far my harnesses have done very well in this department. I'll double up. If I'm using, for example, so it's a rotary, it's a 2-rotor, we got 4 coils. I'm more than likely doing at least 2 14-gauge wires out of the relay to feed the one set of 4 coils. And then it'll split as close as possible to the connector with 16-gauge, and then from then on, we'll do 16-gauge directly to the coil. So I'm usually not getting any voltage drop there.
Yep. All right. So our next little topic here. Go ahead, kick that one off.
All right. So here's what I probably want to see what your take on this is, but troubleshooting ignition and trigger issues, because they seem to sometimes be related. Sometimes people think I can't rev past this point, and they think it's a trigger issue, but the triggers are nice and steady. You have to take it, either it's an input problem or it's an output problem. And then if it's an output problem, half the time it can be a mechanical or a physical issue in the engine that you're not really aware of, and the ECU cannot diagnose this anyway. So what you have to be mindful is, let's say for argument's sake, you're running an engine with pump gas. It's not really that badass or ballistic and power goals, let's say 400, but you rev it and it misses at $5,000 and it won't go past it. The most popular expression I get is, I hit a brick wall. So there's a million things that could be happening. It could be fuel related. It could be ignition related. It could be ground related. It could be anything. So my suggestion to start troubleshooting is, first and foremost, remember what we said before, bad data in, bad data out. So if the incoming signals to the ECU, which help it work, are not good, the outputs will be bad. So let's say you have a problem at 5 grand. Look at your trigger diagnostic, the trigger sync level, trigger sync state, the most important two parameters for troubleshooting trigger. If they're not solid at running and full with the engine turning, your problem is a trigger issue. If they are solid, then the problem is output wise, or even over fueling and tuning. I mean, who knows?
Could be all of it.
Could be all
what
of it.
I do from a tuning standpoint is I'm going to say, okay, we have this amount of sensors. First off, if we have sensor data that gives us exhaust gas temperature and you see EGT dropping, there you go. You're getting something a little bit closer, and you can start pinpointing, okay, it's happening on this cylinder or this rotor, wherever it is. Now, from that, you can check, of course, if your fuel pressure versus your fuel pressure expected are close. Is it a fuel delivery problem? There you go. There's number two. What I think is the first diagnostic I do for purely an output side is I will say, let's go reduce ignition dwell. Let's go 400 milliseconds less ignition dwell first, because if it's an RPM problem, I've already shown you guys these charts where we can easily overdwell a situation to where it is now misfiring or going on into the next event, or the coil itself is running into kind of like a fault. So
or
the first
best
thing
case scenario, the table is underdwelled and you're below what you need to run.
But just like if you were testing, does the car need more or less timing? You pull the timing. So be on the safer side. So the first thing you're doing is you're pulling the ignition dwell out of the motor, and that's going to give you
an improvement or a worst case.
You'll see right away. You're saying, okay, it cleared up. Now it goes to 6,000 RPM, and now it's doing the same wall at 6,000 RPM. Now you say, okay, cool. I figured out it needs less coil dwell to be happy. Now I'm going to continue this shape, and if it gets worse, of course, go the other direction. And there's something that I believe David Mazzei said a long time ago is a fantastic approach. He's like, well, just take big swings at it. And if you have a problem that is
not with ignition timing,
right, not ignition timing, but like, let's say there's a problem we're setting up acceleration enrichment. We're just going to change for just a second.
Yeah.
If you are doing acceleration enrichment and for whatever reason the car is not reacting what you think it should be, just give it a big old smack of one direction. Say, okay, did it make it better or worse? And then you're now able to fine tune that from that big swing. So
yeah, we'll discuss transient enrichment. That's on the fueling side, which is after the ignition.
We'll get there.
But anyway, your points are very valid. So instead of just moving timing around, hey, knock some dwell off, add some dwell in. If you think your table is not that high, let's say for argument's sake, you've got a map that has 2.5 milliseconds, whatever coil you're running. Yeah, a little more there. See if it'll improve. Now, if it doesn't, there are other things that you definitely need to look at. And regretfully, it can't just be a one answer deal. Where's the problem? You have to go in steps. And the suggestion is obviously inputs, triggers, even faulty sensors. You could have the coolant sensor that's putting in too much fuel because it's think the engine's cold. So everything is a point of reference. You need to go in steps. So good input first. Output would at least be guaranteed to be okay if the tuning is fine.
Right. And so on the tuning aspect, if again you're running into this 5,000 RPM wall, well, first thing I do is I pull 4 or 5 degrees of timing. I would check what the wideband is doing in regards to if there's any corrections for my short-term fuel trims, if the targets seem reasonable, if exhaust temperatures are going up or down depending on what's happening. As much input data as you have available, use it. So one thing I always put a trigger on, let's say if we're using Haltech or Link or something, is we have when the even injectors or any sensor is unplugged, it's going to give us a fault code for that sensor. And I have those enabled as an engine protection to where, okay, hey, we've acted like during the middle of this pull, it lost air temp. Well, if it loses air temp, that default air temperature table that it goes to might be reducing fuel. It might be adding timing.
Or increasing fuel.
Right, right. But there have been some default programs that have actually done a adding fuel and adding timing. So if the car acts like it has a very ice cold air temperature, and you have a warm-up procedure that is giving the air temperature an extra bit of timing to stabilize the motor when it's ice cold, that might be something that can actually hurt a motor and do the same thing. So all we're saying is to look at your engine protections, set them up as best as you can to where if something is unplugging momentarily, that you can see it in a fault. And therefore, that's going to pinpoint how you're diagnosing and moving forward with your diagnostic on improving that vehicle's output
And of
safely.
course, one of the sections in this module series will be advanced options, and that'll include engine protection, which is save my motor insurance policy.
.com.
Remember, remember, the motor is more expensive than your ECU. Trust the ECU to be programmed correctly, and trust the person programming it, hopefully he's qualified, to do the good job of saving the motor. And you know, don't shortchange it. A lot of people throw Arduino. Nothing against that thing, but it's not a well-developed ECU with all the advanced features of decades old hardware that has been tried and true and developed over the years. So make sure that your setup merits diagnostics, that it tells you what's going on in the best way possible and helps you protect your engine.
All right, so I think that just about does it for this video. We've done all of our trigger recap. We've done ignition recap, kind of going through coil setups, and we already went over base timing plenty of times to this point. How to choose an ignition system. I kind of gave us a nice overview of coils and the explanation of the timing and such. Claudio did a perfect job blending all this together, which is amazing. And I don't know, we can always get into the actual mapping itself and how an ignition should be mapped out for a car.
You know what? Let's talk a little bit about that.
We've got a few minutes on that. I think we should.
Yeah.
So
I'll do.
Let's go way back.
I'll do my little quickie, and then you do your little quickie.
Yeah,
I'm just gonna do my little thing, and then you do.
Take it away.
So here, so effectively, ladies and gentlemen, usually what you want to see in in timing is most engines tend to kind of respond the same way. So here you can see a nice little 3D table. You've got your idle section down here. You've got your light load, high RPM up here, or deceleration part. And then you have the high-powered boosted section, full throttle, balls to the wall section up here in the upper left hand. Now, depending on how you guys arrange your axes, some people have load up top, RPM on the side, or vice versa. Some people go from upper left corner downwards or lower left corner upwards. It all depends on how you have it. So that'll dictate kind of how the shape is reflected in the 3D view. The point of this is effectively the motor needs more advance under light load conditions. And as you go heavier and heavier in loads, your ignition timing value will be reduced. Now, granted, the engine isn't perfect everywhere. So there are compensations to the load or the torque output of the motor that help you sort of balance out and make it feel good all the way through the rev limiter. So what you'll notice is as load goes up, timing will decrease, but it'll also start to increase a little bit past the peak torque point. This will help the engine breathe a little better up top, and then that way you maintain a stable power curve all the way through the rev limiter. And that's my my two
All
cents,
right.
and I'm sticking to it.
My spiel starts with old school stuff because
There
I
you
like
go. Hit
telling
it.
someone, look, have you ever seen how a distributor works? And they're like, distributor? What? What? All right.
What's that?
Distributors, it's very important. Distributors, you could have a base timing of, let's say, 10 degrees, and then there would be a vacuum advance. So when the engine is pulling more vacuum, this solenoid would open up and it would add ignition timing to that. Light load adds ignition timing. And then there's also what could be weights on a spring configuration inside. So like it expands as the engine is spinning or as the distributor is faster and faster. That is what's called a mechanical ignition advance through distributor. That would be, as Claudia was saying, as you go up in RPM, it's further advancing the ignition by moving those weights out inside the distributor to advance the ignition. So it ends up making a very similar curve to what he showed in his presentation just now, but it's through a mechanical device with vacuum solenoids. Okay. Distributors, if we go back to old school stuff, that's where you get to learn the real fundamentals of EFI. You see how things were done properly with jetting for carburetors, you see how things are properly done with distributors and how timing is set. And for the most part, everything Claudio said right there was perfect. Right past peak torque, because now cylinder pressure is less high than it was at the peak torque location, you can actually add ignition timing to maintain your smooth power output. Your peak torque position is going to be where the combustion event pressures are the highest. So that's why you're likely going to have a little dip in ignition there because it can handle more ignition on either side of that curve. So I think we leave it there for now. We're going to go kick off a little recap for the next video, and then we're going to get rolling on fuel stuff. You guys are going to love this next one.
All right. Yeah. So see you on the next one, people.
Cheers, y'all.